Alrighty, so with this video, what I'd like to do is go ahead and work a couple of examples of using Lagrangian mechanics to solve some of the simple physics problems we've seen in past classes like general physics and things like that. So before I do it, of course, let's go ahead and review what is Lagrangian mechanics all about. So first of all, the Lagrangian is defined to be the kinetic energy minus the potential energy of a system. And so once you have your system and you've defined the kinetic energy and the potential energy for all the particles that you care about in the system, you then use the Euler-Lagrange equations to then derive or get the equations of motions you care for that system. So for instance, the Euler-Lagrange equations say the time derivative of the partial of the Lagrangian with respect to the time derivative of the generalized coordinate, so Q, I call the generalized coordinate for whatever particular system we're talking about. It might be the x direction or the y direction, or if we're talking about the polar coordinates, maybe it's theta or spherical coordinates or whatever. If it's Cartesian, it might be x or y and so on. So generally speaking, whatever coordinate, whatever spatial coordinate is important for the system, that we defined as Q, and Q dot is defined as the partial of Q with respect to time. Okay, where Q prime would be the partial of Q with respect to whatever other coordinate we may be talking about, maybe P, or not P, let's not use P, let's use E. So the time derivative is dot, the spatial derivatives are primes, and here we have the first term in our Euler-Lagrange equation is the time derivative of the partial of the Lagrangian with respect to Q dot minus partial of the Lagrangian with respect to Q. That must be equal to 0 under the assumption we don't have some other constraints, some other external forces attached to our system, like friction or air resistance or things like that. We'll investigate what happens if we include things like friction later on. But for now, given a system undergoing whatever free forces happen to be acting on it, the equations of motion can be derived from this particular set of equations. Now, we may have a system with multiple coordinates, so x and y, or theta and r, or whatever, in which case we'd have a system of Euler-Lagrange equations. So, two sets of Euler-Lagrange equations, or three sets, or whatever. But if there's only one coordinate, which we'll see in these examples, you only have one. And so you'll see what I mean when we do an actual example. So let's try one. Let's try a simple example, which is the simple harmonic oscillator. Simple harmonic oscillator. And for this one, what we'll have is it goes like this. Here we have some spring, and attached to the spring system is some mass m. The spring has a spring constant k, and I'm going to stretch the spring by a distance x, and then I'm going to let go. And of course, what do we know is going to happen? The spring oscillator system is going to oscillate back and forth with some frequency, and I'd like to find out what is the equation of motion for this mass m. That is to say, if you ask me where will this mass be at some time t, this equation will be able to tell you. All right, so how do we solve a problem like this? Well, the first thing we need to do is define what is our Lagrangian. And of course, a Lagrangian is kinetic minus potential. So the first step is, what is the kinetic energy of the mass in our system? So the mass is going to be moving. It's only moving in one direction, one dimension, the x direction. So I only need one coordinate for this problem. And the kinetic energy is 1/2 m times the velocity squared. And the velocity being only in the x direction, I could write it as x dot. That's the velocity squared. All right, so that's the kinetic energy. Now what about the potential energy? Well, the potential energy, that is equal to 1/2 times the spring constant k times how far did I originally stretch my spring squared? Or how far did I compress the spring squared? So in this particular example, my q, my generalized coordinate from here, is x. And q dot is x dot. But in other problems, my q might be theta. Maybe it's the angle that a pendulum makes, or maybe it's some other coordinate. Here the coordinate is the x direction. All right, so I have my Lagrangian. There it is, very nice. Now what do I want to do? I want to insert this Lagrangian into the Euler-Lagrange equations. And the Euler-Lagrange equation says the time derivative of the partial of L with respect to the time derivative coordinate, which is x dot, minus a partial of L with respect to the coordinate itself, that must be equal to 0, because I don't have any constraints or outside influences. All right, so let's go ahead and do this. So I have the time derivative of the partial of my Lagrangian with respect to x dot. So first thing to note, this is the partial derivative, which means I only look at terms that have explicitly x dot. Not x, not x double dot, but x dot itself. So what do I see? I see x dot is written right there. There's an x dot. So the partial of that with respect to x dot will be 2 times 1/2 m x dot. All right, then minus the partial of L with respect to x. So I look in my equation. Where do I see x's? Again, I need only the explicit terms with x, not x dot, x double dot, or anything like that. So the only place I see just a plain old x is right here. So I have the partial of L with respect to x dot. That's going to be a 2 times 1/2 minus, there's a minus right here, k x. Okay, so that's the partial of my Lagrangian with respect to x. All of that should be equal to 0. Let's simplify. I've got the time derivative of the 2 cancels the 1/2, and I have mx dot. And then I have a minus minus is plus. The 2 cancels the 1/2, and I get a kx equals 0. Now, I'm going to assume that the mass in this problem does not change with time. It's just a block. He's not adding mass or subtracting mass. It's not like it's a piece of ice that's going to melt or some rocket fuel that'll be burned off in time. So the only thing in the first term that depends on time is the velocity. So that term is mx double dot. The time derivative of x dot is x dot dot, of course, plus kx equals 0. And then solving for mx double dot equals minus kx. Now this is from Newton's laws. this mx double dot is ma, which is F, the force, and this is the force is equal to minus kx, and that's exactly what we saw from Newton's laws. The force due to a spring is equal to kx, but minus, because if you pull the spring to the right, the spring pulls back to the left. It's always in the opposite direction of what you stretched. So if you stretch to the left, the spring pulls to the right. If you stretch to the right, the spring pulls to the left, and so forth. And of course, we could then say x double dot is equal to minus k over m x, where k over m is related to the frequency of oscillation. And there we go. There is our equation of motion. From there, we could do things like integrate to find the velocity, integrate twice to find the position, and all sorts of stuff. So there's a simple harmonic oscillator. Very easy, not too big of a deal. A little more complicated than just using Newton's laws. Newton's laws just say F equals ma. Ma is equal to the force, and we know the force is minus kx. But here we've derived it completely independent of Newton's laws, and we get exactly the same equation. So very nice. Next example I'd like to do is the simple pendulum. All right, so what does the simple pendulum look like? Well, here's the ceiling, and we have some pendulum, a pendulum bob whose mass is m, let's say. This pendulum string has a length L, and let's say the pendulum is originally moved to the side by an angle theta. And again, what I'd like to do is calculate the equation of motion for this pendulum bob. All right, so how do we do it? Again, the Lagrangian is t minus v. And now we see the first little piece of kind of creativity or artistry that is involved in this new technique of physics. And that is, what coordinates should we use to make this problem as simple as possible? So the first guess would be, well, of course, Cartesian coordinates. We always like Cartesian coordinates, x, y, z, because that's what we're used to with everything in physics. But if I use the Cartesian coordinates, when this mass moves back and forth, of course, it's moving in both the x and the y direction simultaneously. So if I use Cartesian coordinates, I'm going to need two sets of Lagrangian equations, one for the x direction and one for the y direction. And that's perfectly valid. There's no problem with doing it. You can do that perfectly fine. But usually what we try to do is simplify our equations mathematically as much as possible. And when we say simplify, in this context, what I'm talking about is there a way to write this equation in terms of just one coordinate? Instead of talking about x, y, and z, is there some coordinate I can think of, some new coordinate system transformation I can do, where instead of having two equations of motion, one for x and one for y, I can have just a single equation of motion? And indeed I can. That's why I wrote this pendulum is moved by an angle theta, because what I'm going to try to do is solve this problem in polar coordinates. Because in polar coordinates, notice the radius of our mass, that is how far from the center point the mass is constant. It's always a distance L away from the pivot point, because it's always at the end of the string. And of course, I'm going to assume my string does not slack In real life, we'd have to worry about such things, but in this particular case, I'm going to assume I only move it by an angle theta, which is sufficient to not slack the string, so the mass is always a distance L away from the pivot point. But theta will change. So if I use polar coordinates, only one of my coordinates is going to be changing, and that's theta. The r coordinate will not change. Whereas in Cartesian, both x and y will change, while z will not. All right, so I want to write my Lagrangian in terms of polar coordinates instead of Cartesian. All right, that's not such a big deal. So the first thing I need is my 1/2 mv squared. And then my potential will be mgh, right? That's my normal way of doing things. But notice this has nothing to do with polar coordinates yet. So let's write this in polar coordinates. All right, so in polar coordinates, we have 1/2 m. What is our velocity in polar coordinates? Well, again, I'm not moving in the radial direction. That is to say, I'm not moving back and forth this way. However, I am moving back and forth this way. And that's the theta direction. And if you remember, in centripetal motion, in rotational motion, the angular velocity is defined as v is equal to L times theta dot. Or should I say it's the distance times the angular displacement time derivative of that thing. Since my radial distance isn't changing, L is a constant, only the theta is changing. And so theta dot, sometimes you'll call that omega, the angular velocity, only the theta is changing. So for my velocity, it's L theta dot, and then it's velocity squared. Right? So my linear velocity, v, in terms of angular velocity, which is L times theta dot, v is L theta dot, and v squared is L squared theta dot squared. Okay. Then the potential energy, well, let's look at that. The potential energy, what do I have? My mass at this point, let's say at the beginning of my system, I've moved it at an angle theta. How high above the lowest point being down here, is my mass? What is this height h here? Well, it's from here all the way down to the lowest point. That's L. That's the length of the string. My mass can't get any lower than however long the string is, L. But when it gets to this point over here, that height right here, that's L cosine theta, right? If we look at my little triangle, here's a triangle right here. If this is L and this is theta, then this side right here is L cosine theta. So my h is going to be this distance, which is the full L minus the L cosine theta. L minus L cosine theta. And if I write this all out, I have 1/2 m L squared theta dot squared minus mgl plus mgl cosine theta. That's my Lagrangian. Right? Kinetic minus potential. What's the kinetic? 1/2 mv squared. However, I want to write it in terms of polar coordinates. And for polar coordinates, this is rotational motion, centripetal motion. And so the only thing changing in time here is my theta, my angle, excuse me, and my angular velocity. If you think of the distance traveled, that's arc length, r theta. So the velocity is r theta time derivative, but r isn't changing. The length of my string does not change with time, so the r stays the same. That's just L. So the only thing that does change is my theta. So theta dot. So my velocity is L theta dot. So the kinetic energy is 1/2 mv squared, which is m 1/2 m L squared theta dot squared. Potential energy is mgh. But I need to write my h in terms of polar coordinates. So what was h? H was the distance above the lowest point it gets to, because I'm going to count the lowest point as the zero potential energy site. So everything above that, in terms of theta, will be mgl minus the mgl cosine theta. So I write it out. That's my Lagrangian. There it is right there. What's next? Now all I have to do is time derivative of my partial of the Lagrangian with respect to whatever time derivative of my coordinate is. And in that case, it's theta dot minus the partial of the Lagrangian with respect to the coordinate itself, theta. That must be equal to 0. If I were doing this in Cartesian coordinates, I'd have x and y Lagrangian stuff, and so I'd have an x Euler-Lagrange equation and a y Euler-Lagrange equation. But here, I only have one, because the only thing that matters here is my theta. So now all I have to do is plug this stuff in. I've got the time derivative of the partial of my Lagrangian with respect to theta dot. So where are the theta dots? The only place the theta dot appears is right here. So I've got 2 times 1/2 ml squared theta dot. All right, and minus, I've got the partial of L with respect to theta. Where does theta lie? Theta is right here. So it's the partial of that term with respect to theta, which is mgl. The derivative of cosine is minus sine theta. And that's equal to 0. Notice, by the way, this term right here has neither the theta nor the theta dot. So that has no bearing on our Euler-Lagrange equations at all. And this is an important thing. Anytime you have a Lagrangian, you could always add in terms which are constant terms. MGL is a constant. The mass is constant. G is constant. The length of the string doesn't change. That's a constant. You could always add a constant into the Lagrangian and not affect the equation of motion. All right, so let's continue. What do we get here? So the 2 cancels the 1/2. The time derivative, well, mass doesn't change. L doesn't change. So it's just ml squared theta double dot. Then the minus with the minus becomes a plus. mgl sine theta is equal to 0. Assuming the mass is not 0, I have L squared theta double dot equals minus GL sine theta. Dividing the L squared over, I've got theta double dot, is minus G over L sine theta. And that's the equation of motion for my simple pendulum. Now, what we usually do in physics is we say, okay, if I want to try to solve this differential equation, That's the second derivative of theta with respect to time squared equals minus g over L sine theta. Well, this I can't solve normally. This is a transcendental equation. I cannot write down a functional form of this solution. So usually this is where we start making our approximations, which we talked about early in the semester. We might use something like the Taylor series approximation and say, look, sine theta for small angles, I could write it as theta. And so maybe I'll write this as minus g over L theta. And then I could solve this explicitly, functional form solution, for small angle approximations. Or if it's not quite a small angle, maybe I'll keep more terms of my Taylor series and so forth. But if you want the actual equation of motion, this is the equation of motion right here. Okay. And this is how we work our Lagrangian examples, our Lagrangian mechanics. You're going to have a system. You first write down what is the Lagrangian for that system. The Lagrangian being the kinetic minus the potential energies. You usually want to try to discover for this system the most efficient coordinate system for that problem. That is to say, can I find a coordinate system that minimizes the number of coordinates necessary to describe the system? Once you've done it, now you don't have to do that. You could have the most inefficient coordinate system and still work the problem. It's just that if you work with an inefficient coordinate system, you're going to be left with multiple equations of motions at the same time. But if you could find one with only a single coordinate system, a single coordinate that changes with time, then you write down your Euler-Lagrange equations for that coordinate. You solve it, and you'll be left with your equation of motion. Here, in this simple harmonic oscillator, Cartesian coordinate system worked perfectly fine. The mass only moves in the x direction. It's only a one-dimensional problem, so no big deal. Nothing wrong with that. Write down kinetic minus potential, 1/2 mv squared minus 1/2 kx squared, where x dot is the velocity. We then do the Euler-Lagrange equation, the time derivative of the partial of the Lagrangian with respect to x dot, minus the partial with respect to x is equal to 0. And then you go through until you get down to your equation of motion. With this problem, this is a two-dimensional problem. So if we try to use Cartesian, then I'd have x direction stuff and y direction stuff. That's fine, no big deal. My kinetic would be 1/2 mx dot squared plus 1/2 my dot squared. My potential energy would be mgy. And then I'd be left with two sets of the Euler-Lagrange equations. One for the x stuff, one for the y stuff. That's fine. However, if I'm creative, I can find that if I use polar coordinates, then I can actually write both the kinetic and the potential instead of in terms of a single coordinate, theta. Well, if I can do that, then I'll only have one Euler-Lagrange equation to worry about. So I'll only have one equation of motion rather than a system of equations of motion. And so here, that's what I did. I can write the kinetic and the potential in terms of theta and theta dot and so forth. Once I've done that, I then do the Euler-Lagrange equations where theta is my coordinate, and I get my single equation of motion. Unfortunately, the solution here, the actual equation of motion, is transcendental because it has to do with sine theta. And so if I actually wanted to solve this, Usually I do some numerical approximation, Taylor series, Maclaurin series, and so forth. But if all I want is the equation of motion, there we go. There it is. Done. So next time, I'll try to work some two-dimensional problems. What happens if I cannot find a coordinate system which allows me to write this stuff down in terms of a single coordinate? Well, no big deal. We just have two equations of motions with two unknowns. And then we'll go from there. We'll start talking about Hamiltonian mechanics and so forth. Anyway, hope this is helpful. I will see you next time.